In this video, we're going to talk about two main points. First, we're going to contrast three different statistical procedures, namely hypothesis testing, effect size, and confidence intervals. Next, we're going to discuss the basics of confidence intervals. On this screen, I'm going to give you a table that lays out the three statistical procedures as well as their respective purposes. Hypothesis testing, also known as significance testing, has the purpose of deciding if a result is likely or unlikely to be created by sampling error. In other words, is the sample mean different from the population mean? Is the difference between those two likely to be caused by sampling error? If it's not likely to be caused by sampling error, we conclude that it's probably created by the treatment. We could also test to see if one sample mean is different from a second sample mean. Is the difference between those two sample means likely or unlikely to be due to sampling error? Again, if it's not likely to be due to sampling error, then we assume it's probably created by the treatment. Effect size has two purposes. If the hypothesis test rejected the null, saying that the treatment caused the difference, then the purpose of effect size is to describe how well the treatment worked. If, however, the hypothesis test did not reject the null, then the purpose of effect size is to determine if the sample size was appropriate. Again, if you do not reject the null, you might not have rejected the null because your sample size was too small. So if you get a large or medium effect size when you did not reject the null in the hypothesis test, then you know that you should redo the study with a larger sample size. And finally, confidence intervals. The purpose of confidence interval is really to estimate the population parameter. In this situation, you want to know what your best guess is at the value of the mean of the entire population. Now we're going to talk about the basics of confidence intervals. A simple definition of a confidence interval is that it is a range of plausible values for a population parameter. For example, maybe it's a range of values for a population mean. It's important to remember that the range of values are not equally plausible. Values in the middle of the range are considered more plausible than values at the ends of the range. Confidence intervals contain three things. The point estimate is the most likely value for the population parameter. I'm going to describe how you get the point estimate on the next screen. Confidence intervals also contain an upper boundary and a lower boundary. An upper boundary is the highest value in the range that is considered plausible. And the lower boundary is the lowest value in the range that is considered plausible. These two values, or these two upper and lower boundaries, are considered equally plausible. It's just that one is on the high end of the range and one is on the low end of the range. And I'll show you how to find those on a future screen too. All right, let's talk about the point estimate. You're going to be familiar with this logic because we've been following this logic or using this logic for a large portion of the semester. So we have a population, let's say it's a population of 6th graders, and we want to know how well they're reading. We want to know their mean reading comprehension score. Of course, the population is too large for us to actually study the entire population, so we take a sample. After we measure the sample, we find the mean of the sample. Let's say that the mean of the sample is 40. Now what we're going to do is we're going to use the logic of, well, according to the central limit theorem, my sample mean is my best guess at what the population parameter value is. Now we know that this answer isn't going to be perfectly accurate because of sampling error. But it's our single best guess. That's why we call it our point estimate. That's the center of the plausible values, the point estimate. Now there's another way we could use a confidence interval. Let's suppose we take a sample of people from a population, but now rather than measuring them now so that we can figure out what the population parameter is right now, we could treat the sample and then measure them. And so now we get the mean after the treatment. Let's say that now after the treatment we get a mean of 50. Now what we're saying is our best guess at what the population parameter would be if we gave them the treatment, mu sub t, would be 50. Of course, it doesn't have to be 50 exactly. It probably isn't 50 exactly. It's just that this is our best guess based on our study. Again, this would be our point estimate. We always use a sample mean as a point estimate. Now we need to talk about the upper and lower boundaries. The upper boundary is the sample mean, in other words, the point estimate, plus a critical t-value from the table. Now it's important that you recognize that this critical t-value comes from the appendix at the end of the book. You look this up, and the coming activity will tell you exactly how to look that value up and which tables to use and why. The other part of the upper bound is the SEM. Now you know at least 3 different ways of computing an SEM, and you need to use the correct one. You need to use the SEM from a single sample t, or the SEM from a related samples t, or the SEM from an independent samples t. It depends on the kind of confidence interval you're creating. And again, the activity coming up will help you determine which one to use in which situation. The lower bound, again, the lowest plausible value in the range, again, starts with the sample mean, but now rather than adding the product of these two terms, in the lower bound, we subtract the product of those two terms. This term and this term, of course, are the same. It's just we're subtracting in the lower bound from the mean, and the upper bound we're adding to the sample mean. The product of these two terms, excuse me, is called the margin of error. So we take, in order to compute a confidence interval, you simply take the sample mean and you add to it the margin of error, or you subtract from it the margin of error. Let's just do a quick example. So let's say that I took a sample and the mean from that sample was 50. Then, based on the type of confidence interval I want to compute, I look up a critical value in a table. Let's just say that I looked that up and the answer was 2, or the critical t was 2. So I'll put that in there. And let's just say that I computed the SEM and that came out to be 5. Again, a future activity will show you exactly how to do those things. And then I just do the math. And so this 10 is the margin of error. So I'm adding that to the sample mean of 50, so I get the upper bound of 60. Then I have to do the exact same thing for the lower bound. The sample mean is still 50. All the other values are the same, except now I'm subtracting them. And so when I do that, I get a lower bound of 40. Now let's take one more picture just to show you what all this means. This is a distribution of plausible values for the population mean. 50 was our sample mean. Again, according to the central limit theorem, that's our most plausible value. It's the highest. This is a frequency distribution, right? Just like we've been doing for a long time. That's a frequency distribution, and the highest point on the curve is above 50. So that makes it the most plausible value. 40 is considered a plausible value, but it's a lot less plausible than 50. 45, which would be right here, is considered to be more plausible than 40, but less plausible than 50. So as you move away from the sample mean, values become less and less plausible. 40 is considered the lower bound because that's the lowest value that's considered plausible. And 60 is considered the upper bound because that's the highest value that's considered plausible. It is possible that the real population value is out here or out here, but it's very unlikely. Now, how unlikely is it? That depends on the critical t value that you use. And again, a future activity will tell you about that. If you want to have a 95% confidence interval, then that's going to influence the value of the critical t that you're going to use. If you want to have a 99% confidence interval, then that's going to cause you to create a different, or to use a different t critical value. This should give you the basics for how to conduct confidence intervals, and then the details will come through in the activity that you're about to do.